the planning. Because one thing is that now you can do confidence intervals for proportions. So when we have the next election and papers start giving you proportions on polls and all, remember this. I cannot myself see a proportion without immediately computing the standard error of the proportion, right? To make me a bit relaxed about you shouldn't believe it too strongly, right? And especially if you don't like the result, it's nice to have a large interval. Or just to be intelligent. To me, that's intelligence, to realize the value of the numbers that someone hits you in the face with, right? However, when you become the project managers and later managers in the companies where you go, you will also, as I've discussed previously, be managing the budgets for such projects or investigations or studies. So you will have to decide, am I going to ask 100 people, 1,000 people, or 1,000,000 people? And it's pretty much more expensive to ask 1,000,000 people than 100 people. So right, N is money. Size of the studies are the same as money. So we need a way to plan this, to give us the precision that we'd like, but also not much more, if we want to be good about it. So we define exactly with the same words and same ideas as we've seen for the mean in previous chapters. We define this part of the confidence interval. So the confidence interval is p hat plus minus the so-called margin of error, right? That's basically the same thing that we looked at before. So I'm giving that a name because the way we are going to turn it around is that we are going to shuffle this around and isolate n. That's the sample size formula that I'm given here. Because, and then I use the ME, the margin of error, as part of this formula, with the idea that you can turn things around and say, hey, if I want a margin of error on a percentage to be, for instance, and we're going to have a look at that, plus, minus, what did we find? 6%. We had a margin of error in our study from before, right? That's not good enough for me. I want to know the percentage with plus minus 1%, say. How many students, how large a sample should I make to identify with this precision such a proportion? Oh, can you see a problem with this formula? Oh, he asks many questions today. Usually he just talks and we can just sit there. Well, anyway, don't worry. I am having a formula for the sample size to plan a study where the purpose of the study is to determine P. As a part of this formula, to find out how I should determine P, I find P. Bugger. It's circular, right? I need the P to know how large N should be to find the P. That's not good. But that's how sample size considerations often hit us. It's very difficult to speculate on the size of the needed samples without any speculation on what we will meet when we hit the real life in our project and start measuring things. So, we can either use it by guessing some P or scenario-wise speculate on the size of P and then compute the needed sample size. So it's a scenario-based thinking. It might not be the true and right answer to our challenge, but it's the only thing we can do. Or we can do this little magic. You see what I've done here? I have just, instead of P1 minus P, I've put in 1/4. How could I do that? Well, because the function P times 1 minus P, here I use X, on the interval from 0 to 1, actually is a parabola, like that, with a maximum in 1/2, right? That's second year, first year high school function investigation, find the derivative equal to 0. And I think we know the theory about quadratic parabolic functions for you to at least believe me. If you don't see it immediately, I'm sure you can see that you would be if you spent 5 minutes. That it actually, this thing maximizes in 1/2, and the maximal value is then 1/2 times 1/2 is 1/4, right? So we could actually use that as the sort of worst case scenario. The 50% case apparently is the worst case scenario that could hit us for a planning perspective. Let's see how it works. Let's consider the left-handed study. Let me assume that I would like not to have +/- 6%, but +/- 1%. Isn't that a good precision for a percentage, that you know it with +/- 1%? I think it is. What should n be? How large is study? How many should I ask? No, we don't do it Blackboard, so let it hang around there for a few seconds. Look at I plug in the formula. I use it first, speculatively, right? I speculate, I assume, scenario-wise, I say, hey, what if my pilot study is having a bit of a picture and saying, probably it's around 10%. It might not be so, but it's probably around 10%. If I think that it's around 10%, how large a sample size should I take to make a precision of +/- 1% when I've done the study? Well, I plug in my formula. P1 minus P, that comes from this assumption, right? The wanted ME was 1%, and the standard normal, 95%. Since I'm only now talking about 95% confidence intervals, I could talk about any size, but now I talk about 95. And I use the formula, and it tells me, hey, I'm gonna run around in quite a few auditoriums and make the same question here to get such a precision. Please remember that number also. If you see surveys for the polls and elections, that to get something around 10% as precise as +/- 1%, you need 3,000 to 4,000 people in your study. Usually the polls are not that big, actually, generally. And what if we didn't want to make the assumption that we had any idea of what the size of P would be in the beginning? I used the 1/4 instead of the P1 minus P. Whoa, that's expensive not to know anything, right? If you didn't know, and you want to be more or less sure that you would get that precision, no matter what the P that would hit you would be, then you would need almost 10,000 in your sample size to have +/- 1%. That's what you need around 50-50, right? That's 10,000. Please remember that. When 48% out of 500 people say they want to vote for one candidate, well, if you didn't ask 10,000 people, it's a pretty uncertain statement, such a proportion. That was confidence interval, one proportion.